Hello, welcome to this the 36th class in our physics of materials lecture series. In this class we are going to focus on magnetism, as we have already put together a lot of a theoretical background for a lot of the material properties, and we have a fairly sophisticated model, a lot of features for the models that we have, and we are in a position to use those models as we find necessary to explain material properties. So, we will look at magnetism today. We will pull together all the ideas and concepts related to magnetism, and in the end we will see how our current theory that we have developed helps us understand magnetism, okay, or at least some specific forms of magnetism. So, this is what we will do in this class. So, if you look at it, magnetism is basically it's a experimentally observed phenomenon, right. So, we can experimentally observe this, it is a phenomenon where we see materials exerting an attractive or repulsive force on other materials. Okay, so, this is over and above what you may see from an electrostatic perspective. So, let us assume that they are at least the sample that we have is electrically neutral, and still we find that the two samples are able to exert some kind of an attractive or repulsive force on each other, and in general that phenomenon that we see, which is quite commonly encountered, is called magnetism. It has of course a lot of industrial and technological uses. There are many things that we use which have magnets in them. I mean, of course your audio speakers have magnets in them, most motors have magnets in them, and so on. So, we see magnets in various places, sometimes we are not aware that they are there, and of course sophisticated instruments like NMR and so on also use magnets. So, there are a lot of places where magnets are used, sometimes we are aware of them, sometimes we are not, but they are definitely there, and in principle these are this basic idea is what is true in all those cases, okay. So, in this relationship, in this context, we will define specific parameters with which we quantify this magnetism, the phenomenon of magnetism, and then proceed on that basis. So, the first thing that we would like to quantify is something called magnetic field strength. Okay, and this represents the strength of the externally applied magnetic field. So, often we are studying what happens to a material as it interacts with a magnetic field. To study that, we have to actually externally generate this magnetic field, impose it on that material, or make the material encounter this magnetic field, and then study what is happening to that material as it encounters this magnetic field, okay. So, we have to generate this magnetic field from somewhere, and when we do that, the field that we generate is quantified by this thing called the magnetic field strength, okay. Incidentally, as I mentioned here, this is a phenomenon that we observe experimentally, and the way we understand it is that it is associated with movement of electrical charges. So, anytime there is an electric charge that is moving, okay. So, a charge that is moving, associated with that moving charge is this magnetic field. So, it sort of creates this magnetic field around itself as it moves. So, and that is how we experience it, and as such, in a static sense you will only see the electrostatic field, but when it is moving you also see the magnetic field associated with it. So, we have this thing called a magnetic field strength, and a simple way in which this is this external field is generated is by taking advantage of this movement of electrical charge. So, we simply have a current carrying conductor which goes through a coil and comes out. Okay, so we have I goes through this and let us say there are n turns in this coil, and we will also say the length here is L. Okay, so across a length along a length L we have n turns of this coil and the current I is going through that conductor. When you do this we get a magnetic field strength which is simply n times I by L. This is the quantity which we are calling the magnetic field strength. It is denoted by the letter H. Okay, so H is the externally applied magnetic field and is also called the magnetic field strength, and its units are, as you can see, this is number of turns, this is in meters and this is in amperes. So this is ampere turns per meter, that is what it is. So it is in ampere turns per meter. Or simply it is in amperes per meter. So these are the two units in which we represent. So we simply say amperes per meter. So that is what this magnetic field strength H is. Okay. So now as I said, we would like to study what happens to materials when they encounter a H field. Okay, so a H field is there. We bring a material, make it encounter this field. We see how it behaves, and on that basis we say something about the material, or we understand something about the what is going on in that material. Okay. So to do that we have to bring the material into this system and see what is happening. So say for example we can keep a block of material within this coil and then see what is happening. So when this field interacts with that material, it creates a field inside that material, and that we call as the magnetic induction. We call that as magnetic induction. Or we also call it as magnetic flux density. These are designated by the letter B, capital B. Okay, so magnetic induction or magnetic flux density designated by the letter B, and this B is in Webers per meter square. Okay, and it is related to H. Okay, so the H is the field that you are imposing based on the current that is going through the coil, and B is the field that is getting induced inside the sample as a result of the interaction of the sample with this H field, and it is related to the H field by this equation mu H. Okay, where mu is the permeability, is called the permeability of the material. And it is a constant for a material under certain circumstances. So you place it under the same circumstances, it will be a constant. So this is the permeability of the material. Okay, so this is what we have, and you can see the units of mu. It is going to be Webers. So this is per ampere meter, right? So this is what you are going to get. Webers per ampere meter. This is what you will get, Webers per ampere meter. So if you substitute that Webers per ampere meter times amperes per meter, so Webers per ampere meter, this is in amperes per meter, you will get Webers per meter square. Okay, so this is also given as Henries per meter. So the units of that are used in magnetism that way can create some confusion, but you just have to follow them as they are. This is Webers per ampere meter, and it is also called Henries per meter. This is mu, this is the permeability of the material. Okay, so and this is how it relates the magnetic induction, what is occurring to the sample as a result of the field that you have imposed, which is H. Now supposing if you do not have any sample and you just have vacuum, we can still talk in terms of a field that has been induced in that vacuum. And in that case we would call B as being equal to mu naught H if you did not have a sample and you simply had vacuum in the middle of the coil, and this mu naught is then the permeability of vacuum. okay, it is permeability of vacuum. It is useful for us, I mean you may think that that's a situation that may not be particularly useful for us, but in fact it is useful for us because it helps us understand how other materials are behaving relative to vacuum. Okay, so it sort of sets some kind of a baseline. With respect to that, you can say you can sort of gauge what the other material is doing, and relative to that we can scale the other materials. So this is permeability of vacuum. Okay, so this is what it is. So clearly if you have vacuum you are going to get mu naught, if you put some material you are going to get mu. Okay, so we also define something called relative permeability. And which is simply the ratio of the two, it is mu by mu naught, and it is designated as mu r. Okay, so while mu and mu naught both have henries per meter as their units, clearly the ratio is going to be unitless. So this is unitless. Okay, so that is what we have. Now if you look at the material, you take the material, you place it in the magnetic field. Okay, so it is responding to the magnetic field. So what normally happens is in some there are phenomena occurring within the material which is either assisting the magnetic field or trying to oppose the magnetic field. Okay, so we can sort of look at the response of the material and it is in that sense that we actually compare the material to the response of vacuum. So we say the vacuum would respond in a certain way, is the material adding to that response or is it subtracting from that response. So that is what we can designate it as. So we call that response the response of just the material as magnetization. Okay, and it is the manner in which it is adding or subtracting from the system. So what we basically say is that we have originally written B as mu h, where we have permeability of that material times the field that we have imposed on the material. We can instead write it as a component, given that you already have the field h, vacuum in that location would have given you mu naught h, right. So we can separate the component from the vacuum, mu naught h, times plus mu naught times some other parameter m. So we are basically saying that this is the component coming from the vacuum, mu naught h, plus this is an additional component over and above this vacuum response, which now represents the extent to which the material is assisting or opposing the process. Okay, so this is mu naught m. This m is the magnetization, m is called magnetization. Okay, this m also we can further relate to, so we just we'll add one more quantity here and then we'll write a couple of equations which will simply rearrange these terms. We can write m itself, now I have written this as though it were independent of the external field, but actually it is also a result of the external field. So in some ways you can relate it to the external field again, you can make this as some constant times the external field in that sense. So we can write the same equation as mu naught plus mu naught h plus mu naught times chi times h, where this chi h is simply telling us that the magnetization that has occurred in the material has not occurred sort of in an independent sense, it has occurred as a result of the field that you have applied. So we are recognizing that by saying that it is something related to h, it is chi times h is how we are relating it. So we have now these two equations which are both equal to b, and of course that is itself equal to mu times h. So we originally started with b is mu times h, we incorporated, we said that consists of a component that would anyway have been there if vacuum had been there, and a component that would exist if which is simply because that material is adding or doing something over and above vacuum, and that again we are relating to some with the mu naught times something, and that something is again related to the field that you have put in. So given that we have these equations, we can just rearrange a little bit. We have h is a common here, so we are simply saying mu, so mu h equals mu naught h plus mu naught chi times h. This chi here is called susceptibility, okay, magnetic susceptibility. So chi is magnetic susceptibility, mu naught is permeability. So that is permeability of vacuum, mu is just permeability, mu naught is permeability of vacuum. So if we have this equation, so if we remove H, we simply have mu is equal to mu naught into 1 plus chi, okay, and therefore and mu by mu naught is relative permeability, that is how we have defined it, implies mu r equals 1 plus chi or chi equals 1 minus mu r, I am sorry, mu r minus 1. Okay. So these then are the equations that we have a few equations we have put down here. So we have this susceptibility is also unitless, okay, so it is a unitless parameter, the relative permeability is also a unitless parameter, these are both unitless parameters. So we wrote H as Ni by L, we wrote B as mu times H, in which the B due to vacuum is mu naught H, right, and then we wrote mu by mu naught equals mu r, this is the relative permeability, and we also recognize that chi is mu r minus 1. So these are the parameters that relate to magnetism and tell us about various quantities in magnetism. They tell us what are the quantities that we should be watching out for in magnetism. These are the quantities that people have sort of isolated in this magnetism phenomena, so that if you follow these parameters you can say something about the material, you can compare materials on the basis of these parameters, on the basis of the values of these parameters for those different materials. So this we can do, okay. So so these are the equations that we will use. Now the magnetism itself, so we will look at this, so this is what we will use, this is these are the equations that we will pull out as and when we require. Now the thing we have to see is, now we would like to see a material and we find that it has a certain response to a magnetic field, we would like to explain why this is having this response, what is occurring in the material that is creating the response. Now inside the material, therefore we would like to understand what is the charge that is moving, so that we can now say that the magnetic field is related to that charge, and therefore we can now see how that magnetic field responds to the field that is being externally applied to it. So inside a material we typically have electrons which are now the charges that are in motion. You can have an electron having orbital movement, and we can also have it, so you can sort of think of it as though it were running around in an orbit, although that is a very simple way of looking at it, and we can also have it spinning around its axis, okay. So in both cases we have a situation where there is a charge that is moving, so associated with both of them you have magnetic moments. Okay, so we have magnetic moments associated with both of them, and basically what we say is that we in fact we associate what is called a Bohr magneton as the most fundamental magnetic moment. It is associated with the spin of the electron, it is represented as represented by mu b, and it is about 9.27 into 10 power minus 24 amperes per meter square. Okay, so so that is what it is, and so this is the magnetic moment associated with the spin, and the orbital magnetic moment is typically mi times mu b, where mi is the magnetic quantum number. of that electron. So for a given electron we can identify its magnetic quantum number, and therefore mi times mu b would then be the magnetic would be the contribution of the orbital moment of the electron and the magnetic moment coming out of it. Okay, so this is the picture of what is happening within the material, which then represents and then you have to add this up to get the magnetic moment of the overall material. And simply these are all vectors you have because of spin and the movement of the charge, these this has a quantity, these are all vectors, these both have quantities and a direction associated with them, they are vectors, and the net magnetic response of a material is the vectorial sum of the response from all the magnetic moments present within the material. Okay, so you have to actually identify all the sources of magnetic moments within the material, and you can add them up vectorially. When you add them up vectorially, whatever result you end up getting then represents the net magnetic response of that entire material. Okay, so that is how it is going to be. So this is what is existing within the material, and so when you subject it to a H field or H field, what you see is a response coming from here. Now again amongst the materials, what is going to happen is based on the orbital moment of electrons, in fact there are going to be orbital moments of different electrons which will be in opposition to each other. As a result, the magnetic moments from those electrons will cancel each other out. Okay, similarly if you have electrons with in terms of spin, they can have a spin up or a spin down. So the Bohr magneton contribution from the spin can be in the form of plus or minus mu b. Okay, so if you have a pair of electrons with one with having the plus mu b contribution and another with minus mu b contribution, they will cancel each other out. So in fact for atoms which have fully filled shells, fully filled electron shells, atoms which have fully filled electron shells, the net magnetic moment is 0. Okay, so this is true for example for the noble gases, so helium, argon and so on, right. So for these there is no net magnetic moment because the shells are completely full, which means all the contributions from the orbital magnetic moments cancel each other out, all the contributions from the spin magnetic moments cancel each other out. At the end of it you do a vectorial sum, you get 0, and therefore there is no net magnetic moment. But there are a variety of materials where either the orbital magnetic moment will not cancel itself out completely, or the spin magnetic moment may not cancel itself out completely, or both. Okay, so this can exist, and it is on that basis that you may have a variety of materials where the individual atoms may have a net magnetic moment. Still the sample itself may still be neutral because those magnetic moments may be randomly oriented. The sample consists of a large collection of atoms. So for the sample again you have to do a vectorial sum of the magnetic moments of all the atoms present within that sample, and if they are all randomly oriented and their values are the same, they are again going to cancel each other out, and so at the end of it for your sample you may have a net magnetic moment that is 0. So you have three cases: you can have the atom itself having a net magnetic moment 0, you can have atom having a net magnetic moment not equal to 0 but the sample having a magnetic moment equal to 0 because they are cancelling out on average, and the third case where neither the atom has a net magnetic moment that is 0 nor does the sample have a net magnetic moment that is 0. So there is some finally there is some magnetic moment still left on the sample. Okay, so we have all these possibilities that exist. So in this context we have different forms of magnetism which are exhibited by materials. One is diamagnetism. This is actually in fact almost all materials show you some level of diamagnetism. The only issue is that it is such a weak form of magnetism that in most cases other magnetic phenomena in the material completely swamp this contribution, so you will not see it. Okay, so you will not see it in most samples simply because other phenomena are more powerful than this in terms of strength. So in fact you actually only see it in cases where you have been able to eliminate all other forms of magnetism in it, and then therefore you see the magnetic moment the diamagnetism stand out. So this is absent in the presence of an external field, in the absence of an external field. And weakly opposes the field when it opposes an applied field. Typically the contribution is from the orbital magnetic moment of the electrons. They are so if you look at a situation where all of them are originally cancelled, they are so the atoms are all neutral, so you will have a series of atoms which are all neutral, and then when you apply a magnetic field, it interacts with the orbital magnetic moment of those atoms, and they try to oppose this imposed magnetic field. Okay, so they now stand in opposition to this field, but it is a very weak interaction. Okay, so therefore it tries to oppose the magnetic field and tries to reduce the strength of the magnetic field. Okay, so what we are basically seeing is that relative to vacuum, so if you look at mu by mu naught, which is equal to mu r, if there were no sample, you will only see mu naught, right. So that is what vacuum would do. Now we have put this sample and it is opposing the magnetic field in a very weak way, so therefore this mu is going to be less than mu naught. Okay, so it is trying to, the B that it is creating is less than the B that would exist, the induction, magnetic induction that would exist in the when vacuum is present, which would be mu naught H, and the magnetic induction which is now present because the sample is present, which is mu times H. This mu times H is less than mu naught times H, and that is how it conveys to you that it is opposing that field, right. So that is why you are getting a little less field there than that, you are getting a little less induction there than you would if you had vacuum. So mu times H is less than mu naught times H in this case, which I mean, since H is a constant, it simply means mu by mu naught, which is this relative permeability, is less than 1. So for diamagnetic materials, mu by mu naught is less than 1, mu r is less than 1. So similarly, and therefore chi, which is mu r minus 1, is negative. So you see that in fact this gives you an example. As we look at other examples, you will see mu r therefore can be less than 1, equal to 1, or greater than 1, and chi can be negative or positive. Okay, chi can be negative, 0 or positive. So this is the range that we have available to us. So it is negative, but I also said that this is a very weak phenomenon, extremely weak phenomenon, and in a relative sense, I mean, so the chi value actually works out to of the order of 10 power minus 7. This is unitless, it is on a per volume basis, but still we will just it is fundamentally unitless, so it is 10 power minus 7. We will just keep that number in mind because that is what we will use for comparison, 10 power minus 7. This is for diamagnetic materials. Okay, so originally the atom is neutral, that is when this even shows up in any sense as being, because that is the only response it has then. So the originally it's magnetically, there is no magnetic moment from the for the atom, all the other moments have been cancelled out. When you apply the field, the orbital moments become apparent, but they oppose the applied field, and then you see this response. Okay, so this is what we see for a diamagnetic material. The other material you can consider is a paramagnetic material. This is paramagnetic material or paramagnetism exists in materials where there is an net uncancelled magnetic moment either of spin or orbital origin. It does not matter what is the origin, spin or orbital, net magnetic uncancelled magnetic moment is there on a per atom basis. However, the sample is has no magnetic moment in the absence of an externally applied field. Okay, so in the absence of an externally applied field there is no net magnetic moment in this material, but at an atomic level there is a uncompensated or uncancelled magnetic moment either from uncancelled spin moments or uncancelled magnetic I mean orbital moments. So that is there at an atomic level. However, those atoms are all randomly oriented, or the magnetic moments corresponding to those atoms are randomly oriented in that sample. So as you look at the sample, as such there is no magnetic moment in the absence of a field. Okay. Now if you apply a field, what happens is these uncancelled magnetic moments align in the direction of the field. Okay. So in some of these materials it is seen that they align in the direction of the field, and so we again we get B is mu h, and of course we have mu by mu naught equals mu r. In this case since they are aligning in the direction of the field, okay, and it is adding to the field. Okay, so it is strengthening the field in the region where the sample is present, because these moments are aligning in the direction of the field. Therefore the mu h is going to be greater than mu naught h. Vacuum would have provided you with mu naught h. When now that you have put the sample, the uncompensated or uncancelled magnetic moments present within the sample are aligning in the direction of that magnetic field and adding to that field, and therefore it is the overall magnetic induction in that location is higher than what would have been the case if you had had only vacuum. So mu is actually greater than mu naught, so therefore mu r is greater than 1, and chi, which is simply mu r minus 1, is positive. Okay. However, this is again this phenomenon is still again a very weak phenomenon. Okay, so it is a very weak phenomenon. So in fact this is chi is a positive value, but it is still of that order, it is of the order of 10 power minus 7. So whereas so it is simply that here it is plus 10 power minus 7, and in the case of a diamagnetic material it is minus 10 power minus 7. Okay, so of that order we are looking at. So it is a negative value for a diamagnetic material of the order of minus 10 power minus 7, and for a paramagnetic material it is plus 10 power minus 7. So these are small numbers in the relative sense. When we look at other systems we will see that there is a difference, and but it is a positive number. The other thing that is common about both paramagnetism and diamagnetism is the fact that both of these are phenomena that are visible only when a field is applied. Okay, so when there is no field that is applied, the material is neutral. So even a paramagnetic material, if you stop the field, the minute you stop the field, they will again go back to a random orientation. All the magnetic moments will go back to a random orientation. So for the sample you will have no net magnetic moment. Same thing with diamagnetic materials. Even though they are opposing the field, the moment you stop the field you will actually lose the magnetic moment, the orbital moments will disappear, and you will anyway have nothing in the sample, no magnetic response left in from the sample. So therefore both paramagnetic materials and diamagnetic materials are in that sense also referred to as non-magnetic materials. Okay, they are both non-magnetic materials. So this is non-magnetic. Both para as well as diamagnetic. Both of them are non-magnetic materials. Okay, so because they do not have any magnetic induction left in them the moment you remove the externally applied field. Okay, so that is why. So therefore they are not actually of in terms of technological interest, they are not that of great significance from that sense. The next type that we are interested in is the ferromagnetic material. This is actually available in there are a couple of other sub classifications of it, but we will look at the main classification of the ferromagnetic material. It is one where you mostly have uncancelled the magnetic moments of there are each atom has a magnetic moment, typically due to uncancelled spin magnetic moments. But the main difference here is that even in the absence of field, the spin magnetic moments actually interact with each other in their neighborhood, and several of them begin to align with respect to each other. Okay, even in the absence of a field. So there is an cooperative arrangement of the such that there is a net magnetic field, net magnetic response, magnetic moment even in the absence of an applied field. I must qualify this a little bit because you can sort of force a situation where this drops to 0, you can force a situation where this net magnetic moment will drop to 0, but in general it will have a net magnetic moment, and if you can always stop the magnetic externally applied magnetic field at some point, the sample will be left with the magnetic moments that got aligned as a result of the applied field. Okay. So the cooperative arrangement of the spin magnetic moments occurs at various regions within the sample, each region may be randomly oriented. So again we have to do a vectorial sum. What we will typically see is that in general for the sample something will remain, and that is the ferromagnetic behavior that we are talking about. So in this case when you see when you write B equals mu h, I mentioned that you can think of it as a contribution due to vacuum mu naught h plus mu naught m. This is the sample's contribution to the magnetic behavior that you are seeing in the presence of the magnetic field, applied field. Okay. What is happening in a typical ferromagnetic material is that this value is very large relative to what vacuum would do. Okay. A vacuum will give you some response, whereas mu naught m is much larger than mu naught h. So for a ferromagnetic material this is simply approximately just directly equal to mu naught m. And what is m? M is itself chi times h, so it simply means that we have a very large value of chi. The susceptibility, magnetic susceptibility of a ferromagnetic material is a very large positive number, and in a relative sense this is of the chi here is of the order of 10 power plus 6. Okay, so for a paramagnetic material it was 10 power minus 7. Okay, and for a diamagnetic material it was a negative quantity minus 10 power minus 7. So that is what we had for those two, but so they are very small quantities relative to what you are looking at here, 10 power 6. So this is 13 orders of magnitude difference in response, right. So that is what we have here, that is how this material differs from paramagnetic or a diamagnetic material. So in fact if you see if you make a plot of B versus H, so this is the field you are applying, this is the field that is getting induced in the sample. If you make this plot, what you see is for vacuum you will see a response here, a diamagnetic material will have a response which is less than that of vacuum because it is actually opposing the field. So a diamagnetic material, but it is a very weak response, will show you a response like this, this is diamagnetic. Again, and when you remove the field this would drop to 0, abruptly it will drop to 0. If you suddenly switch off the field here, this will drop to 0. Paramagnetic material is slightly better than vacuum because it is assisting the field that is applied, but it is again a very weak response, so that this is paramagnetic. Again when you remove the field, if you come up to here in H and you switch off the H, it will just drop to 0 because there is nothing and it is in that sense that a paramagnetic and a diamagnetic material are non-magnetic. A ferromagnetic material would look like this. Okay, a ferromagnetic material would look like this. So this is this means that for even for small h you are getting a very large B, and that is why it is much larger than the vacuum's contribution. This is not even really drawn to scale, it is simply drawn as a schematic to convey the idea to you. And also in the ferromagnetic material the other important thing is if you bring h up to here and then you abruptly switch it off, what you will see is that a fair bit of magnetism remains in the material. Okay, so we do not actually lose the magnetism, it sort of remains in the material. That is the fundamental way in which a ferromagnetic material differs from a diamagnetic and a paramagnetic material. Even amongst the ferromagnetic materials you can have another two variations on it. One is called an anti-ferromagnetic material, and another one which is called a ferrimagnetic material. The common thing between these two is that it so happens that in these two materials the cooperative alignment of spins occurs in an opposing manner between adjacent atoms. Okay, so the moment from one atom opposes the moment from the next atom, which is in out of phase with the moment from the third atom, again out of phase with the moment from the fourth atom, and so on. And so therefore the even though the atoms have net magnetic moment, even in the absence of a field, they are actually cancelling each other out. Okay, so they are in opposition, so they cancel each other out. If the atoms are of the same kind, they are of the same valency and so on, they will cancel each other out perfectly in this, and that would then be called a antiferromagnetic cancellation is complete. Okay, so if the atoms are of the same kind and you have the same number of atoms and you have same valency, all those things are same, and they were aligning themselves in an opposition in a cooperative manner, they will all cancel out and you would get an antiferromagnetic material, which is where the cancellation is complete. On the other hand, you can also have this kind of a coupling, except that the cancellation may not be complete because maybe the atoms, neighboring atoms are of a different kind, or maybe are of a different valency and so on. And so you will still be left with some net magnetic moment, and that is the ferrimagnetic material. Cancellation incomplete. However, they are all in the sense that there is a net magnetic moment associated with atoms even in the absence of a field, in that sense, and there is a cooperative alignment of atoms across some distance. In that sense they are all subsets of ferromagnetic materials. Okay, so this is what we understand of ferromagnetic materials. So we will add one more detail about magnetic materials to our picture, and then we will look at how the theory is helping us understand it. Of course this is got to do with how the magnetic materials respond to the field H. So we can write draw H versus B plots, and what you will see, this is for a ferromagnetic material. Okay, so for a ferromagnetic material, as you raise H, you actually see a response that looks like this. Okay, this actually represents the fact that as you initially within the sample already there is the magnetic moments are the atoms are cooperatively aligning with respect to each other, neighboring atoms, but that occurs only over a small region. So if you have a large sample, several small regions can be oriented in different directions, so the net magnetic moment may be close to 0 or 0, and then as you put the H field, more and more of those regions align with respect to the H field till you reach a point where all the regions have aligned with respect to the H field, and therefore that's the saturation that you can get in it. Okay, saturation magnetization. If you reverse the field, you will see a behavior that looks like this. So this is the behavior that you will see, and again you can write permeability here, which is simply if you write B is mu times H, right. So clearly at each place so B versus H, if you look at the slope for B versus H, that slope is what the mu is, that slope is varying, and so this is called mu I, or the initial permeability. Okay, and so this is how this behavior is, and it is in this context that the materials this is called remanence, this is called Br remanence, this is in the negative direction minus Br, this is coercivity Hc and plus Hc. This means once you have magnetized it, even if you drop the field to 0, some amount of induced magnetic field remains in the material. That is what the ferromagnetic behavior is all about. So that field remains in the material. Now to remove that field, you have to actually put an opposing, remove that induction, you have to actually apply an opposite field of this strength before that induction drops to 0. That is coercivity. Okay, and similarly when you return, again you will have in the opposite direction the induction, and the you correspondingly raise the field in the positive direction before you can cancel it. So this is what this is how a ferromagnetic material responds to changes in field. Depending on the material you choose, you can actually have systems where this is very narrow or this is very wide. Okay, very narrow but steep, which means high initial permeability but very small amount of coercivity. Okay, so you can have a situation which looks like this. You can have a situation which looks like this. Okay, so this is a steep climb here, so that means mu I is very high, high initial permeability but very small coercivity. You can also have magnetic materials where you can have this to be the situation. Okay, so here in terms of initial permeability, if you are looking at this direction, it is a lower initial permeability and high coercivity. The inner curve here is what we would, a material describing displaying the inner curve is what we would describe as a soft magnetic material. A material describing displaying the outer curve is what we would call as a hard magnetic material. So for magnetic storage, something, so a hard magnetic material would retain, once it is subject to some magnetic field, it would retain a certain state, okay, much better. Even with some changes in the its environment, it will retain that state. You have to make significant changes to its environment before it loses its magnetization. Whereas the soft magnetic material, even with small changes in the field around it, the induced magnetization induced magnetic field will drop to 0 quickly. Okay, so this is for a soft magnetic material, this is a hard magnetic material. This is preferred for things like materials which are being used for applications such as transformers, where you have to keep changing the field applied through it several times, and you do not want to lose energy. This represents energy being lost to the system. The outer curve would then represent places where you want the magnetic behavior to stay much after you have removed the field. So for magnetic storage, this would be much more appropriate. Okay, so this is what we have. Now in terms of what we have already discussed, we drew for our systems density of occupied states as a function of energy, and we saw this curve, okay, and at some Fermi energy E equal to EF. So this is energy and this is E equal to EF. So this is the density of occupied states, this is what we drew, and this represents the states of the electrons. Now I also said that this if you put we included spin in it, so we actually had 2 times this number of electrons actually. So okay, this is the density of occupied states, actual number of electrons is twice this, and that is because you have spin up and spin down. So pictorially we'll do 2 things. Pictorially we'll just first of all flip this picture around. So we will have a picture that looks like this, with E on the y axis and N of E on the x axis. And additionally what we will do is, instead of simply saying that there are 2 electrons per state, we will represent it like this. Okay, so these are with spin up, these are all the electrons with spin up, and these are all the electrons with spin down. It is simply a representation as a function of energy density of states. We are simply representing this as spin up electrons, these are spin down electrons, let us say. That is how we are representing. Half of it is spin aligned in one direction, half of it is spin aligned in the opposite direction, and we still have the Fermi energy. I will just alert you to the fact that this sort of looks like a E versus K curve. This is not an E versus K, I mean this is not that curve that we are talking of. This is E versus N of E curve. Okay. Now when you apply a magnetic moment in terms of the theory that we have developed so far, the way the material is responding is something like this. What is happening is the states that are aligned with respect to the magnetic field are going down in energy, so they become more stable with respect to the field that you are applying. The states that are having a spin opposite to the direction in which you have applied the magnetic field go up in energy, so they become less stable with respect to the energy, they become less desirable. And but at the same time I mentioned that the Fermi energy is something like a chemical potential. If chemical potential of two regions goes up, then material will move so that the chemical potential once again equalizes. So what will happen is electrons from the higher energy level will shift towards the lower energy level till the energy is minimized. So our picture after we apply the field will look like this. Okay, and let us say this was our original EF. So what will happen is we have shifted up by this much. So actually if we had not done any changes, the electrons, so this is spin opposite, so spin moment opposite applied field, and this is in direction of applied field. Parallel to since this is parallel, this is now going down in energy, this is opposite, the spin is opposite to the applied field, it is going up in energy. If you just maintain the entire set of electrons to be the same, so what was the Fermi energy here now just moves up here, and what was the Fermi energy there moves down here. So now we have this set of electrons which are having, so this is now sort of the Fermi energy of the electrons which are in opposite the applied field. This is the Fermi energy of the electrons which are along the Fermi in parallel to the Fermi parallel to the applied field, and this situation cannot be sustained, which because it means within the system we have two different Fermi levels that cannot be sustained. These electrons will move such that the Fermi level becomes the same, because that is the chemical potential of the electrons and it cannot have a difference. Difference will enable them to move. So these electrons will simply move here. Okay, so you will again come back to some level that looks like this, because these electrons would have moved here, and so this is what you will have as your final state within the material. Okay, your original state was like this. Temporarily you got a state where this went up and that went down, but then electrons moved so that your final state is like this. So you now have more electrons in the occupying the states which are parallel to the applied field, and therefore this explains to you how alignment of the spins with the applied magnetic moment occurs. So you see now how the theory that we have developed and the diagrams that we developed and so on help us understand what is happening in the system. Okay, so we will conclude today's class by just summarizing that we have now looked at magnetism as a phenomenon. We have looked at all the major parameters associated with magnetism and the various phenomena of magnetism, how it manifests itself under various circumstances, and what happens when you take different materials and subject them to variations in magnetic field and such. And we have also seen how we can understand it in sort of in some ways from a classical sense, and in some ways based on the theory that we have developed so far, and so we get some sense of how to understand magnetism as a phenomenon and the science behind magnetism. So with that we will halt today and we will pick it up in the next class. Thank you.